Welcome to the new topic. Today we are discussing PN junction diode. We have already discussed the two types of extrinsic semiconductors, P-type and N-type. A P-type semiconductor is made by doping with a trivalent impurity and holes are majority charge carriers in P-type. And an N-type semiconductor is made by doping with a pentavalent impurity and electrons are majority charge carriers. Now consider a P-type semiconductor. On one side of this semiconductor, we are doping with any of the pentavalent impurities. So we get a new crystal, one side of which is P region and the other half is N region. And in between, we have a boundary, we call it as junction. And that junction, it is PN junction. We cannot form a PN junction by simply joining P and N type back to back. We will not get a PN junction. It should be formed metallurgically. That means in one crystal we have to dope with the pentavalent or trivalent impurity. If we try to make a PN junction by keeping P and N type semiconductors together, the surface irregularities prevent the contact at the atomic level. So we will not get an exact PN junction. Now in this PN junction diode, on left side we have P-type material and the right side we have N-type material. In P-type, holes are majority and free electrons are minority, and in N-type, free electrons are majority and holes are minority. When we look at the concentration of holes on P region, it is higher concentration, and on N region, the concentration of holes is less. And in the case of free electrons, there is higher concentration of electrons in the N region and smaller concentration of electrons in P region. So, because of this difference in concentration, we say there exists a concentration gradient across the junction, and because of this concentration gradient, holes diffuse from P region to N region and the electrons they diffuse from N region to P region. So diffusion of mobile charge carriers takes place because of this concentration gradient. Since diffusion of free electrons and holes take place here, their movement constitute a current. Effectively, the current due to these two diffusions will be in the same direction, and that current we call as diffusion current, and it is in the direction from left to right. That means from P to N. This crossing of majority charge carriers takes place in the nearest vicinity of that boundary, in the middle. So, when holes diffuse from P region to N region, actually the acceptor atoms will be in the negatively charged state. So, because of the diffusion of holes, there will be a layer of acceptor atoms which are negatively charged on left side of the boundary. Similarly, on N region, that means on the right side of the boundary, there will be layer of positively charged donor atoms. So these acceptor atoms and donor atoms, they are the dopant atoms in the P-type and N-type semiconductors we have already discussed. Because of the formation of these layers of negative charge and positive charge on either side of this boundary, there is no mobile charge. We know the mobile charges are free electrons and holes. In the nearest vicinity of that middle boundary, there are two layers on either side of that boundary which is devoid of any mobile charge carriers. There are only the immobile charges which are the positively charged donor atoms and negatively charged acceptor atoms. There are no free charges or mobile charges in that region. That region which is depleted of mobile charges, that region is called as depletion region. And because of the presence of immobile acceptor atoms and donor atoms on either side, there exists a difference in potential on either side of that middle boundary. That difference in potential we call as barrier potential. So on left side we have low potential and on right side we have high potential, and that potential difference is called as barrier potential. Because of the positive charge in the N region and negative charge in the P region, An electric field will be formed whose direction is from positive to negative. So from N to P, in that direction, electric field will be formed. So the free electrons from the P region will be attracted towards the N region. Okay, and likewise the holes from the N region will be attracted towards the P region under the action of these electric field. So this movement under the action of electric field, we call it as drift. So we can say that there takes place a drift of minority charge carriers from P to N and N to P. And this movement or this drift of minority charge carriers constitute a current called drift current, which is in the direction from N to P. And we can see that both diffusion current and drift current, they are opposite in direction. So in the beginning there was only diffusion current, and as the time goes this diffusion current decreases, and we can see that there forms a depletion region in the nearest vicinity of that middle barrier, and drift current starts flowing, and drift current it increases. So when the diffusion current decreases, drift current increases, and at one particular point both these currents which are in opposite direction, they become same in magnitude. Therefore the net current flow across that barrier in the middle will be equal to 0. So we say the equilibrium is reached, and we say that PN junction is formed. So the important processes involved in the formation of a PN junction, it is diffusion and drift. Now here we have the symbol used to represent a semiconductor diode, and this is how it looks. The black region it is P type, and the silver layer it is N type. So we conclude the two important processes that occur during the formation of a PN junction is diffusion and drift. Diffusion occurs due to the difference in concentration of the mobile charge carriers on either side. So electron diffuse from N to P and holes diffuse from P to N. Effectively, the diffusion current is in the direction from P to N. Due to diffusion, a layer of positive charges, which are positively charged donor atoms, appears on N side of the junction, and a negatively charged layer, which are the negatively charged acceptor ions, on P side of the junction. The space charge region, which is depleted of any mobile charges which appears on either side of the junction together, is known as depletion region. So important point to remember, in depletion region there are no free electrons and holes. So as the diffusion process progresses, the positive charge on N side of the junction and negative charge on P side of the junction develops an electric field. Due to this field, an electron on P side of the junction moves to N side, and a hole on N side of the junction moves to the P side. That means the minority charge carriers, they move across the junction. The movement of these minority charge carriers due to this electric field is known as drift. So as the diffusion process continues, drift current increases, and we can say diffusion current decreases. This process continues until the diffusion current equals the drift current. And at that point, when diffusion current becomes equal to drift current, we say equilibrium is reached and there is no net current across the junction, and we say PN junction is formed. Now, the potential difference produced due to the diffusion of charge carriers across the PN junction is called as barrier potential, and this potential barrier or barrier potential limits the further diffusion of holes and electrons across the junction. So that is why that word barrier. A PN junction with metallic contacts provided at the ends for the application of external voltage, we call it as semiconductor diode. So simply a semiconductor crystal which is made as a PN junction diode with the metal contacts on either side, we can call it as a semiconductor diode. So it is a two-terminal device, and the symbol is this. The triangular portion stands for P and the straight line stands for N. And this potential barrier, the barrier potential is a characteristic of a diode. If the diode is made of germanium, that potential barrier will be 0.3 to 0.4 volt, and for silicon it will be 0.7 volt.